Here in the first part of lesson 2, we're going to be talking about confidence intervals for proportions. We've got 3 learning targets that we're going to be going over. So learning target 6, state and check the random check, the 10% check, and the large counts conditions for construction of a confidence interval for a population proportion. So you remember those 3 things from when we did population proportions in chapter 7. Learning target 7, determine the critical values. Remember that was a big piece of the margin of error for calculating a C% confidence interval for a population proportion. We're of course going to be using technology. And then learning target 8, construct and interpret a confidence interval for a population proportion. That's the big thing that we'll be doing today. Learning target 6 and 7 will basically just be leading up to that. All right, so a couple things for vocabulary first. Number 1, we've got a few things that we need to check before we can do anything really. And so conditions for constructing a confidence interval about a proportion. Well, first thing is we need to check that it's random. And we're going to be able to check if it's random if we somehow say it's a random sample. So usually you'll see the phrase or the SRS, simple random sample. And as long as our samples are being collected randomly, then that checks out. Another thing that we have to check out is the 10% rule. So I forgot to put that in here, but the 10% rule. The 10% rule is going to be found if our population, we'll call it big N, is greater than or equal to 10 times little n, our sample size. And of course, this is basically our check for independence so that we can use our formula for the, I guess it'd be p hat, our formula for standard deviation. And then we've also got the large counts condition, and this is what we use to find if it's approximately normal. Right? So nothing that we don't get to use normal CDF unless we can assume that it's normal, and the way that we find that it's normal is with the large counts condition. And so with proportions, that's n, the sample size, times our proportion. Now, of course, we don't actually know the true proportion, so we're going to use p hat, which is what we have, and this has to be greater than or equal to 10, and then the complement, so n times 1 minus. Again, we don't have the true proportions, we're going to have to use p hat, and this also has to be greater than or equal to 10. So we've got 3 tests to check for to see whether or not 1, it's random, 2, it's independent, and 3, it's approximately normal. And then we'll have one big formula for today. So it's called a one sample. So again, we don't have many samples, we have one sample. It's called a Z interval for a population proportion. And this will give us our confidence interval, so interval, confidence interval for a population proportion. So we're going to take p hat, which is our point estimate, and then plus or minus, and here's the margin of error. We're going to get the z-score, and so in this case, to indicate that it's a little bit different from just regular z-score, but we're going to put z-star, and then times, just like you saw in the first lesson, the standard deviation. Of course, since we've got a proportion, we're using the standard deviation formula, so that's p hat. Again, we don't know the actual proportion, that's why we're using p hat, times the complement, 1 minus p hat, divided by the sample size. So this is our point estimate, okay? And then here is our margin of error, and we're going to find the margin of error by finding a z-score and then multiplying it by the standard deviation. And that's how we find the confidence interval for a population proportion. So lots of different examples here. So this first one, check whether each of the conditions is met. And so this is just getting to learning target 6. So Latoya wants to estimate what proportion of seniors at her boarding school like cafeteria food. So we've maybe seen this one before. She interviews a simple random sample. Okay, so random, check. We've got it. It's random, says right here. And then we want the independence. And so that's going to be the 10% rule. And, well, let's see, our sample size is 50. So n equals 50. So is the overall population, which is going to be the 175 seniors, is this greater than or equal to 10 times the sample size, 50? Well, let's see, and the total is 175. So is 175 greater than or equal to 500? And the answer is, well, no. So this does not pass the independence test. And I guess, once that fails, we can't really do a whole lot. But just for practice, what about the test for approximately normal, the large counts condition? Well, the large counts condition, here we've got 14 out of the 50. So 14 out of 50 would be approximately 2.28. And so we could just go ahead and say n times p would be 50 times 0.28, and looks like that would be 14. And that is greater than or equal to 10, so that checks out. And then we have to do the other one, n times the complement, 1 minus p, I guess it's p hat, isn't it? Okay, and so again, we'll go ahead and do our calculation here. We've got 50 times the complement, 0.72. And if you do that calculation, you get 36, which is also greater than or equal to 10. So while it passes a few of the tests, it does not pass the 10% test. And so we can say ultimately, no, we cannot check or use this information. All right, here's another good one. Just getting to kind of the nuts and bolts, this would be learning target 7 in a nutshell. Just find this z-score that we would use to get a 98% confidence interval using our calculator. So this is how we get it. This is our critical value. So we'll say z star, and we're going to say, well, if the whole area underneath the curve is 1, and we're taking out 98% of that, that would leave us with 0.02. And then we're going to split this up so it's on either side. So if you think about it, we got the normal curve. Okay, we got two ends. I want 1% on this end and 1% on this end. So I'm dividing it by 2. So 0.02 divided by 2 is 0.01. And again, we want to find the z-score. And so we're going to use inverse normal. And the area that we're looking for, so we'll say area, is 0.01. And then because we want the standard, or the z-score, we're going to say that the mean is 0 and the standard deviation is 1. And so when we put that into our calculator, we're going to wind up getting a little bit of an awkward negative 2.33. And we're going to turn this into positive 2.33. And what does that mean? Well, that's, remember when we were trying to find z-scores, that's what we used inverse normal for. When we had the z-score, that's when we used normal CDF. And so this is our critical value. Okay, we're going to have to go 2.33 standard deviations away in order to get a 98% confidence interval for whatever context this problem has. All right, let's see. So I got 3 parts here. This is really getting at the heart of our lesson, learning target 8. Again, we're going to prom, and we got 750 seniors. We did a simple random sample of 50, and we got 36 planned to go. So part A, what is the population? Well, the population is seniors at her school. And what is the parameter of interest? Well, our parameter is going to be the proportion of seniors going to prom. Okay, that takes care of part A. Part B, check the conditions. And so the conditions here, again, we've got 3 of them. Does it pass the random check? And do we see anything here? Yes, we do. This passes the random check, and so, yep. And then the 10% check to see whether or not it's independent. And, well, let's see, remember that is the population has got to be greater than or equal to 10 times the sample size. And so in this case, we have 750 seniors. And so we've got 10 times 50. Well, in fact, 750 is greater than or equal to 500. So this passes the 10% check, and we can say that it is independent. All right, and then finally the large counts condition, which is going to tell us whether or not it's approximately normal. Here we're going to just say, all right, well, if we've got 36 out of the 50, that's going to be 0.72. So there's our p hat. And so we've got 50 times 0.72. Is this greater than or equal to 10? And let me check here. Looks like 36. So, yep, 36 is greater than or equal to 10. That checks out. And then 50 times the complement, which is 0.28. Is that greater than or equal to 10? And we get 14. And so again, this checks out. All right, so we've got everything that we need here to actually get started working. And so part C says construct a 90% confidence interval for P. Well, we've got a little bit of our work taken care of. And so the first thing we want to do is get that Z star. Right? What is the number of standard deviations away that I need to go in order to get a 90% confidence interval? So in order to do that, remember from last time, we're going to do inverse norm, which is what we use to find a z-score. And then in this case, our area that we want, basically on either side, the remainder left over would be 10% divided by 2 on either side is going to be 5%, so 0.05. And then again, we want the standard deviation to be, the mean to be 0 and the standard deviation to be 1. And when you go ahead and plug that into your calculator, you're going to get negative 1.64. So in essence, we are 1.64 standard deviations away from the mean in order to get a 90% confidence interval. All right, well, here we go. This is what it's going to look like. I remember that formula for a one sample thing. That was the mean proportion, the proportion. And so in this case, it's 0.72. We found that earlier. That's our point estimate. And then plus or minus the z star score, which is 1.64. and then we're going to multiply that by the standard deviation. We're going to find that using the standard deviation formula for proportions, which is the square root, and then we've got our proportion 0.72 times the complement 0.28, and then divided by the sample size, 50. All right, and we'll just kind of take it for granted that you can put all that stuff together, and we'd wind up with 0.72 plus or minus 0.104. And the typical way that we would put this is like an ordered pair. So our bottom, 0.72, we would subtract 0.104, and we'd get 0.62. And then the top, we would add 0.104 to the 0.72, and we'd get 0.82. And, for part D, it says, interpret the interval in context. Well, I've kind of run out of room, so I'll just say it. Maybe you can write it down somewhere. We just say, we are 90% confident that the proportion, the true proportion of seniors wanting to go to prom is between 62% and 82%. All right. Our final one is more or less just a repeat of this one with maybe a little bit more context. Again, first thing is let's go ahead and find the population and the parameter. So population, okay, in this case, we are looking at U.S. college students. And what is the parameter that we're looking for? Well, we want to know the proportion of binge drinkers. Okay, so we've got that out of the way. And then next we need to do all of our checks. So random, is this random? Well, randomly selected. So yep, that works out. And then the 10% condition to see if it's independent. Well, let's see, we did 5,914 students. And so is the total population of college students greater than or equal to 5,914 times 10? Well, I don't know exactly how many college students there are in the United States, but I'm willing to bet that there is more than 59,000 of them. There's probably more than 59,000 that just go to Alabama. So, yep, that checks out. And then the large counts condition to see if it's approximately normal. Okay, well, we can find our point estimate with the proportion here. We'll say 2, 3, 1, 2. Divide that out by 5,914. And we get 39%, 0.39. And so we're going to take this is 0.39 times our sample size, 5,914. Is this greater than or equal to 10? Yeah, it is. And then the complement, 0.61 times 5,914. Is this also greater than or equal to 10? Yeah, that checks out too. And so it has passed the random test, it's passed the 10% test to check whether or not it's independent, and then it's also passed the large counts condition, which tells us that it is just fine to assume that it's approximately normal. All right, so we want to, now that we've got all that out of the way, we want to calculate and interpret a 99% confidence interval. We want to be really sure of our data. And so, again, we're going to go ahead and find that z-star score. How many standard deviations away from the mean are we going to have to go to get a 99% confidence interval? So we're going to say 1 minus 0.99 is 0.01. And then we're going to divide that by 2. So 0.01 divided by 2 is a minuscule 0.005. All right, well, now we're going to do the inverse norm step to find that actual z-score. So inverse norm, and then we're going to say 0.005. The mean is 0, the standard deviation is 1, and we're going to wind up with, let's see, it looks like negative 2.58. So we're going to have to go 2.58 standard deviations away to get a 99% confidence interval. All right, now we're going to do that test, or at least kind of put the whole confidence interval thing together. So the confidence interval is going to be our point estimate, 39%, 0.39, plus or minus, and then we've got our z-star score, so 2.58, and then times our standard deviation. So remember this part right here gets us our margin of error, and so it's big old square root, and then our proportion, 0.39, times the complement, 0.61, divided by our sample size, 5914. And again, we'll just go ahead and assume that you can do the basics here. So our confidence interval is 0.39 plus or minus 0.016. So our margin of error is 0.016. And that means our final confidence interval, we'll write it like this. When we subtract 0.016 from the 39%, we get 0.374, and then 0.406 when we add it. So again, to interpret it, again, we would just use this phrase. We'd say we're 99% confident that the true proportion of binge drinkers for U.S. college students is between 37.4 and 40.6%. Now the analysis piece here asks us, says a newspaper article claims that 45% of full-time U.S. college students are binge drinkers. Use our result from Part A to comment on this claim. Well, 45% isn't even close to our maximum score, and so we can be quite certain that these people are making stuff up. Again, I've run out of room here, so I won't write that down, but you can go ahead and write something to that effect, that this newspaper article is not telling the truth, primarily because we are 99% confident that the maximum would be about 40.6, 41, so 45%, way out there. All right, that's it for the first part of Lesson 2, Confidence Intervals for P.